Okay, so before I explain what a negative feedback circuit would be in terms of op-amp, let me just give you a general definition of negative feedback. Negative feedback basically refers to having the system auto-correcting itself when a stimulus or an input is placed on it. So something like a pendulum, if you would see, if you would put a force on a pendulum, and then let's say it would swing one way, well, then the negative feedback would be auto-correct, return it back to its initial position. And something like a positive feedback, on the other hand, which we don't really explain in circuit form because it's basically not that much use, would be like a falling object. You push an object, and then it falls more down, and then that causes it to fall more down, and then it just keeps on going. And we call that a positive feedback. So like to define negative feedback in terms of a circuit, here what we're trying to do is have a voltage input going into the op-amp, and then controlling the output based on how we return the signal back to the input itself. So initially, if this was, let's say, ground, then we would have an output of ground. But as soon as we start applying a voltage here, what's going to happen is that this signal will try to cancel out the effect. And if you remember in the past video, I explained to you the two rules of an op-amp. And basically, one, no current going in. And the second rule was the voltage across these two terminals must be the same. For an ideal op-amp, these two must be the same. So, but then how does that happen? When you have a voltage here and you have a ground here, how come these two be the same? Well, that's the point of a negative feedback. What a negative feedback is doing is saying, once you change this from a ground to a voltage source, how can you keep this point zero? This system is going to balance out, counteract the effect of this voltage source. And so we're going to derive an equation on how you can relate that to amplification. By the way, there's a proof behind it why it would turn to zero. But for this course, really, we don't need to derive a proof of why it would be zero and how the negative feedback counteracts. So you would need to know, you go into op-amps and gains and a lot of math around that. So I'm just going to show you, using those two rules, how do you define amplification. Okay, so as you can see here, current in has to equal to current out. Current 1 must equal current 2. So we have current going here, and we have current going in here. So we have a plus and minus. I'll label this plus and minus, and label this plus and minus. That means current, if current goes in this way, I'm going to call this I1, and I'm going to call this I2. Because fundamental rule says no current is going to go in here, then the current going in here must equal the current coming out through here. So, but what is the current going in here? Well, you can use Ohm's law to relate it through this part. Well, the voltage across these two is Vs. The voltage drop across the resistor is Vs minus, well, the rule says 0, because this is ground, so this must be 0. So Vs minus 0 is just Vs. And then divided by the resistance, which is the input resistance. Input resistance, but usually it's called R1 or R2, whatever it is. And must be equal to I2. And I2 would be, well, this is 0 minus V out. This is V out. And divided by the feedback resistance over here. And if you rearrange this equation, put the RF over here, you have RF Vs over Ri, and this is negative, so just multiply by negative. You have VO is equal to negative RF over Ri Vs. This over here is your gain. And you can see this is negative. What does that mean? This is an inverting amplifier. And you can see that because the Vs is attached to the inverting input, the negative. But what if we play around with things? What if we attach the voltage source to the positive? Okay, what if we attach it to the positive? So here, what we're gonna do is the same thing as the other op-amp, except now instead of the voltage source being here, we're gonna put the voltage source here. So keep this as constant ground, and keep the voltage source here. So how can we define the amplification using the same principles that we have applied before? Well, this is I1 and this is I2. We don't know current is going through here. which means Vs is at this node. This node is Vs. That's the voltage at this point. Then through Ohm's law, I can say then plus minus, current going through this way, voltage drop is 0 minus Vs over Ri. And that must be equal to Vs minus V out over Rf. Now this is going to be 0. If I put the Rf over here, I'm going to have Rf over Ri Vs, negative Vs. If I put the Vs on the other side, I'm going to have negative Rf over Ri times Vs minus Vs. I can factor out Vs. And then I'll have negative Vs, 1 plus Rf over Ri. And then, as you can see, because Vi was negative, I'm just going to multiply with negative to get that negative away. I have the output equal to 1 plus the feedback resistance over the input resistance times Vs. Here is your gain. And you have to memorize these two, because these are going to be the most fundamental ones we're going to work with. And you really don't want to derive them every time. It's just simple. If the voltage source is connected to the negative terminal, then it's negative Rf over Ri. That's the amplification. And if it's connected to the positive terminal, then it is 1 plus Rf over Ri. And voltage follower is... voltage follower basically is a circuit that takes the voltage at one point, in this sense here, Vs, and it will output V out with an amplification of 1, known as unity gain. And so if Rf and Ri are both 0, if Rf is 0, that's the key here, Rf is 0, Ri really, it wouldn't make a difference with Ri. If Rf was 0, then we would have V out equal to Vs, and so we call this a voltage follower because it acts like a buffer, basically. This voltage source would produce the output on its own voltage source, and it wouldn't be dependent on the voltage source being produced by this Vs.